Okay, going back to review just basic absolute value equations, the most basic setup, the absolute value of x equals 2. And we can think of it as a compound OR scenario because when I'm solving for the answers, x equals 2 or x equals negative 2. And on a number line, I have negative 2 and positive 2. And absolute value in this situation is just describing how far away from 0 a number lies. And here I can see I'm 2 units to the left, here I'm 2 units to the right. So my solution set for a problem like this would be positive, negative 2. 2 units away from the center. A little equation, I have x minus 2 equals 8, or x minus 2 equals negative 8. Solving for x, I can see that x equals 10 or x equals negative 6. So a number line representation, solid circles, no shading arranged between because it's 2 exact values. Or in set notation, my solution set is negative 6, positive 10. And the brackets denote set notation as opposed to just plain old parentheses, which denote an ordered pair. Okay, the last example in solving, I have 3x minus 2 equals 1, or 3x minus 2 equals negative 1. So 3x equals 3, therefore x equals positive 1, or 3x equals 1, x equals 1/3. So for my number line, I have 1/3, I have 1, solid circles, and we'll go back and review this. We actually touched on this first semester, but the center of this number line would be the mark at 2/3. I'm 1/3 away to the left, and I'm 1/3 away to the right. And you may remember this from first semester, we ran across a word problem. The distance from the center to each solution is what the equation is set equal to divided by the coefficient. So 1/3 would be the center point on the number line to represent this. And we'll go back and talk about that in class a little more. Okay, moving to the new topic. Absolute values that are greater than the number that we're comparing them to. And we're going to think of this as an OR scenario. So when I set this up for solving, I have x plus 4 is greater than or equal to 10. So I keep the absolute value set up exactly as it's given, but I remove the absolute value bars. Now my second equation, my OR, I still copy what's inside the absolute value bars as it's given, but now I flip the inequality symbol and I set it equal to the opposite number. So here I flip and I take the opposite value. Solving both of these equations, or inequalities rather, and draw a little number line, mark it up. X is greater than or equal to positive 6. That's a solid circle, shading in the positive direction. Less than or equal to negative 14, solid circle, shading in the opposite direction toward negative infinity. And I clearly have a defined, unmarked, uncolored range. And so here are my two answers, represented as inequalities and represented on a number line. Before we can apply what we just did in the last example, the absolute value has to be completely isolated. So step number 1 in number 7, this is actually number 17 on the other side. The first thing to do is subtract the 3 from both sides, leaving you with this. And now I must divide by the 2 or multiply by 1/2, leaving me with this. This is what I take for comparison's sake. So this is telling me that x is greater than or equal to positive 6, or x is less than or equal to -6. So here I did a flip of the symbol, and I'm taking the opposite value. And now I just simply need a number line for marking. First inequality, x is greater than or equal to +6, solid circle, shading in positive infinity, and then the opposite scenario, solid circle, shading toward negative infinity. And I clearly have an unmarked region, so this is my classic OR scenario. The last example in this column, before you can do anything, you have to isolate the absolute value. So let's subtract let's subtract 3 from both sides, leaving you with this inequality. And now we can apply the method. 2x minus 5 is greater than or equal to +11, or 2x minus 5, flip your inequality symbol and take the opposite. So here I did a flip, and it's the opposite number. So I simplify each inequality, or draw a number line, graphing the first, less than or equal to -3, solid dot above -3, shading toward infinity, and greater than or equal to +8, solid circle at 8, shading toward positive infinity. Clearly have an unmarked region for my OR scenario, classic OR scenario. The easiest way to memorize this, the R in OR and the R's in the greater than. And we'll talk about that more in class. Finally, the last scenario, when you have an absolute value that's less than, you can think of this as a classic AND compound, and take what's inside the absolute value bars. So the first written exactly as is, and it's applying the same method as before. You flip the inequality symbol, set it equal to the opposite, solve each piece. Draw an absolute value bar, or draw a number line rather, mark it up. But now my answer is a range between the two numbers. So this is my classic AND scenario. Here's an alternative method that only works with the AND scenario. You can write this like a classic AND problem, and the way you would do it, since it's set, the inequality number is +10 here, we can create the three-way equation, the three-way inequality. I can have -10 less than or equal to what's inside my absolute value bars, which is less than or equal to +10. And we can solve this just like we've solved the three-way compound inequalities. We would add -4 to all three pieces. So -10 plus -4 is -14. X is now isolated, and +10 plus -4 gives me 6. And it's easy enough to draw your number line representation. And this is your classic AND scenario range. And finally, the last scenario, or the last problem, which is exactly like the other example. Just to give you another example, this is number 18 on the other side. I have x minus 5 less than or equal to 4. So taking what's inside the bars, no change to the inequality symbol, and no change to the number sitting out there. Now, when I make my other comparison, I flip the inequality bar and I take the opposite number. So here my solution set is x is less than or equal to 9, and x is greater than or equal to +1. I could also have solved this setting up the three-way inequality, -4 less than or equal to x minus 5, which is less than or equal to +4. And when I isolate the x in the center, I end up with exactly the same results.